Welcome to my students and researchers. So today we are going to learn how to generate high frequency PWM and with defined switching frequency. So normally we know we are going to learn it through Atmega 328p. So already you can see my videos about PWM and sine PWM, where we are defining the resolution and the frequency of the PWM through the waveform generation bits which are there in TCCR A and B register. Okay, so here we will be generating a high frequency or the predefined PWM signal through timer timer 1. So this I will be showing you through phase correct mode, because to generate the date time the phase correct PWM is only applicable. So let us first see the code. So you can anyway, this is not for the beginners who are dealing with PWM, for them only. So here as we are using timer 1, so it having two channel A and B. So this channel A is, you see, OCR1A is PB1 and OCR1B it is PB2. So in the data direction register, the bit 1 and 2 are set high to define it as output. Now remaining all these things are same, but here just we will see the waveform generation mode. Okay, we will see that. So that waveform generation mode, it will, because we have to find out the timer counter control register A and B. So TCCR1A, let us find it. Okay, so my PC is very slow. You see, in TCCR1A there are two bits, the two LSB, WGM11 and WGM10, and TCCR1B, the fourth and third bit, that is WGM13 and WGM12. So the upper the MSB, upper two MSB will be bit 4 and bit 3 of TCCR1B, and the LSB, 2 LSB, it will be 1 and bit 0 of TCCR1A. Okay, so from here it is clear, this two. Let us see the WGM setting. So now coming down, you see this is the waveform generation mode bitwise description. So we are going to use a PWM in phase correct mode, where the top value of the PWM, it will be taken from ICR1 register. Okay, so this is this bit, sorry, this bit. Okay, so this we are using sequence 10, which is 1010. So now if you see the TCCR1A bit 1 and bit 0, it is 10, and bit 4 and bit 3 also 10. So which is confirming the waveform generation mode number 10. In that case, whatever you are defining in ICR, so let us see what is ICR. Okay, so that is input capture register. You see, this is the input capture register. So in that case, if we are selecting that mode 10, then whatever you are defining in ICR 1 register, that will be the top value. Means timer will say I am defining the ICR 1 value is 100. So timer will go from 0, it will count from 0 to 100. Okay, and now the question is how the PWM frequency will change. How the PWM frequency will change. So that is given by the, you see, this is the data sheet. You see, this is the phase correct mode, phase correct PWM mode. This is the timing diagram, and this is the PWM frequency. Okay, so the PWM frequency in that mode, it will be given by the microcontroller clock divided by 2 divided by the prescaler. Here I have used the prescaler 1 and the top value. In this case, we are taking the top value from ICR 1 register. Okay, so let us see an arbitrary value we take. ICR value let us take as 20. So this will be our, what should be the time period. So the system clock is 16 megahertz. So 16 by 2, it is 8 megahertz, divided by prescaler 1, it is again 8 megahertz, divided by the top value. Top value is 20. So if you do that, so you will get the frequency, and if you divide it by if that is divided by 10 to the power 6, sorry, 10 to the power 6 by that value, it will give us the time period, and the inverse of that, it will give the frequency. So now in ICR, if I keep the value 20, so it should give 400 kilohertz. Sorry, 400 kilohertz. Yeah, it should give the PWM frequency of 400 kilohertz, which is nothing but the time period is 2.5 microsecond. So you see, in the ICR register I have given value as 20, and the two channels I am giving the 50% duty cycle of 10. Okay, 20, 50% is 10. So let us see what is the PWM we can get it. Generally, it should, as per the calculation, it should give 400 kilohertz, which means the time period is 2.5 microsecond. So we emulate that and we will check it. Okay, so now I will now I will run it. Now let us see what is the, so this is one cycle. So if I keep there, you see it is 2.5 microsecond. Let us change it in value. So arbitrarily you take 45. So 45 means it should come around 178 kilohertz, and the time period is 5.6 microsecond. So just I will change it as 45. So I am just changing the input capture register value, and that is based on my waveform generation bit setting. That will be the top value of my counter timer. Okay, Now you see this is 0 and this is my 1 period. You see it is 5.6. As per the calculation it should be 5.625. So anyway, this is that much resolution is not there in this software scope, so that's why it is correctly coming. So this is basically the procedure to change the PWM resolution and the frequency. As we are changing the top value, similar way we can change the bottom value also. Okay, so that we will be learning in the subsequent lectures. This concept is very much useful to generate the PWM signal for multi-level inverter. Okay, where the carrier frequencies are not from 0 to certain value, it will change in between, and that will be compared with your modulating signal, modulating sinusoidal signal. So all these things we will learn later. So today discussion was very limited. It was all about how to change the top value of the timer, and based on that how to generate high frequency PWM signals. So here one thing we understood, that if we want to generate the if we generate the PWM of higher frequency, then the resolution will come down, and vice versa. If you want high resolution PWM, so definitely we have to sacrifice the switching frequency. It is inversely proportional. So for a microcontroller, the PWM frequency and the resolution is inversely proportional. Okay, so all have understand the concept. Thank you so much. Thanks for your patience.